Welcome to Simbeor. We develop and distribute Simbeor electromagnetic signal integrity software. This is a demo of skin effect in microstrip line. I will use Simbeor version THz here. So to illustrate skin effect, I created a kind of problem for analysis of a segment of the microstrip line. Simbeor actually extract per unit length parameters, and shorter segment can be simulated, but for purpose of this demonstration, that's what it is. So segment here is a stack up. There is an air dielectric layer, then signal 1 mil signal layer, FR4 layer 4 mil, plane layer 1 mil, and another air layer at the bottom. So the plane doesn't go all the way through to the side walls, so it's cut here. Materials are defined as FR4 is wideband debye, dispersive model. Copper is just regular conductor model, not a Drude model. We will simulate it up to 100 GHz only here. So segment itself is defined as about 50 ohm impedance, 7 mil wide, and Simbeor 3DTF solver is used to solve it, to simulate it, and to extract parameters and to compute fields. There are two simulations attached here. One is without fields and one is with fields at 9 frequency points, starting from 1 kHz and from 1 kHz to 100 GHz. There are two ports in the structure. Port 1 will be excitation port, 50 ohm with 1 volt source in series, and port 2 will be terminated with 50 ohm. Side walls are perfect magnetic conductors here, just to avoid current flowing on the surfaces other than the signal conductor and the return conductor. And top and bottom walls are also defined as perfect magnetic conductor here. Okay, let's just get started, and I can see the hint that I need verify simulation model. And this is the model, only the elements that are in the conductor are shown here, so I'll uncheck meshed model and compute field views. And the first I'll compute it at 10 GHz electric field in the volume, just to get a sense what it is. Click OK and see the results in the morning, in the moment. Sorry. Okay, instantaneous, and we can see arrows here. Each arrow corresponds to the strength of the electric field at a particular point. Length and color are proportional to the value of the strength of the electric field in volt per meter. So we can see that the wave propagates from port 1 to port 2 here, and electric field changes the direction with each kind of half of the period, and this is a fraction of period here, animation. Density of the arrows means nothing, so errors are in the middle of each element used in computational model. So next, let's compute magnetic field at the same in volume, at the same 10 GHz frequency, and animate it. And we can make it kind of in different color, just to distinguish magnetic field from electric field here. You can see that the fields, electric and magnetic field, are actually orthogonal at each particular point. Doesn't look really good in monochrome. They are orthogonal. Simbeor THz finite elements used by 3DTF solver allows us to compute values of the field exactly with computer precision, obviously. But the solution of the boundary value problem is approximate. So the approximation here is not in the computation of the field. So this is a kind of advantage that we can see the fields everywhere with high precision inside the element, inside each element. This is magnetic field separately. You can see how it circulates around the conductor with each circle, with each period of the field. So next, let's take a look at how power flow through the structure. This is going to be Poynting vector, and at different locations in the space, in the volume, and we can see how more power flows along the edges and below the strip in the dielectric. And it flows in one direction. If you take a look simultaneously with electric field changes the direction, but power flow in the same direction from source to load. If you compute current density, and let's start from the surface current density, you'll see that the current actually changes the direction, but power still propagates in one direction. So we can distinguish it again, trying to like this. So the power is in black and white, and you can see that it always points it in one direction. So next, let's compute current density in a cross section. This is now we're observing surface current density, and which is approximately the same as magnetic field closer to the surface of the conductor. So we can see they are on the same scale here. What about the and they are measured both in amperes per meter. So what about current density in a cross section, volumetric current density in a cross section, and with adaptation to conductor boundaries? And now we can see the skin effect. Now we can see detailed picture of how the current distribution takes place inside the conductor. We zoom in, and we can observe that some currents are kind of lagging behind inside the conductor. The skin depth here is 0.026 mil, so it's very thin layer on the surface. If you take a side view, we can see that, well, this area is really kind of, the skin depth is almost vanishing here, but simultaneously you can see how the current lags behind inside the conductor, and more current flowing at the edges and more current flowing at the bottom surface of the microstrip. So it would be interesting to see how it interacts with magnetic field and compute magnetic field, the same cut plane, and make it a little arrows a little smaller just to fit all those instantaneous. Now we can see interaction of magnetic field with the conductor current. About power flow, instantaneous. This is how power flows, and we uncheck those. This is power flow, it flows the same direction, and we can basically, if you look at in logarithmic scale, you can see that the power flow not only in the direction of the wave propagation, but also in direction perpendicular to conductor boundaries. So basically some amount of energy is absorbed by the conductor, and pointing vector points inside the conductor, and those inside, just immediately inside the conductor. So obviously it's kind of on much smaller scale, but we can still see how it happens. So now let's observe currents in the same cross section and different frequency. Current density at 1 kilohertz and instantaneous value. You can see that the current basically distributed very evenly in the conductor, and the value, if this value multiplied by cross section, you'll see that this is 0.01 ampere, 1 volt in series with 250 ohm resistances. So and with color map we can see how even, and with peak value we can see that this is almost uniform distribution here. A little bit of current crowding here, but not really much, so pretty much the same. Let's move up to 1 megahertz, same current density and instantaneous. 1 megahertz we see more kind of uneven distribution, more current crowding in the plane. So the current actually flowing through the thickness of the plane, so not some delays and current flowing further from the conductor. That would be interesting to see together with magnetic field. And with on a smaller scale. Animated. And we can switch here to color map. And you can see how magnetic field now actually penetrates inside. Comparing to 10 gigahertz, it's just all over the conductor here. It's 1 megahertz, and you can see magnetic field gets into the conductor also, so we can see it everywhere, and on the other side of the conductor, in the matter of fact. So next let's take a look at (100 megahertz) current density. And instantaneous value. So now we can see that skin effect forming, and there is not much current penetrating through the conductor here. We can still see a fair amount of current inside the conductor, and we can clearly see this current lagging behind inside the conductor. Again, we can observe it together with magnetic field. And switch this to color map. This is a skin effect. And together with electric field. And animate it. So now all the fields are in the cross section. Overlap with the current density inside the conductor, without current density. We can see it clearly. Magnetic fields and electric fields interacting with each other. So what about 100 gigahertz? How it's different? Well, there is some gain current density up to conductor. Uncheck all other. instantaneous. Well, obviously skin depth here is much smaller. It's 0.0082 mil. It's barely visible. In addition to all other effects of current lagging behind and really kind of small layer on top, we can also see wiggling between the current direction is not exactly along the edges, it goes up and down slightly due to high order modes, redistribution of current between bottom and top part of the microstrip. So now let's see how the current gets at different frequencies. So for instance, current density at 100 megahertz here. You can see how it gets into the conductor at 1 kilohertz right here. Okay, and we can instantaneous color map. It's 1 kilohertz. One megahertz. 100 megahertz. Ten gigahertz. You can see very thin layer. And finally 100 gigahertz. And with a color map, I'm afraid it's barely visible here. The skin, and you can see current kind of uneven distribution on top bottom sides. This is the end of the presentation. Thank you. To learn more, visit Simbeor.com. Application notes, webinars and knowledge base sections. Or download and try Simbeor now. It is available in download section. Thank you.